this Max tutorial, we're going to create a Voronoi tiling effect. So before we start, let's quickly go over what we're trying to achieve here. So to create a Voronoi diagram, we can place random points on our 2D texture and then divide the space into regions based on the distance from those points. Essentially, each pixel within a texture asks the same question, which is, which point is closest to me? But we're doing it a little differently here because we're taking an input texture and then we will color those regions based on the input texture. So the idea is to downsample a texture into distinct cells. Then we will place 1 point per cell, depending on the color of the cell. Of course, each point has a position and a color, and then for each pixel we will see, okay, which point is closest to this particular pixel and color it accordingly. So for each pixel we will first try to figure out which grid cell it is in. Then we will look at the cell and its 8 neighbors, and then of course each cell has a point inside it and a color. Then we will find the closest point and use that point's cell color. This tutorial consists of 3 parts, I would say. And in the first part, we're looking into how to loop over all the neighbors of each cell. In the second part, we will, for each of the neighboring cells, sample a point within the cell and then check the distance. And in the third part, we will get the smallest distance to the point and then color the cell accordingly. I will start with a JIT world object as our rendering context because we're working with textures. This is a JIT P window to monitor what we're doing, and here I have an input video. So the thing with Voronoi noise is that you can easily achieve it in Max with the built-in jit.gl.pix. So let's quickly take a look at that. So I will first create a texture. Set the dimension to full HD, depth 0. Then we can plug this in here. Take a quick look at the output video. And in order to just get the regular Voronoi, you can use jit.gl.pix. Plug this in here. Then we can set the basis to, where is it? Noise Voronoi. And then let's change the zoom a bit. And if we send the message time, for which we could use no, not text file, but jit.time, we can also animate this. Okay, so this would be a basic Voronoi diagram. But now I want to do essentially what's happening in here, but based on the colors that we're getting from this texture. So in order to do this, let's create a jit.gl.pix codebox object. And then the rest of the code will live in here. Okay, plug this in here. Okay, starting with the first part, which is looping over all the cells. In order to do this, let's first create a parameter for the number of cells. Let's just call this one num cells. Let's say by default that this is 16 by 9 because this is also the aspect ratio of the input texture. Then let's also create our UV coordinates. So we can say UV equals norm, so normalized coordinates. Let's also set a dummy output for now. So output is 1, so this should be white. Okay, perfect. Let's also create UV coordinates based on the grid. We could call this one just grid UV. This is our UV coordinates multiplied by the number of cells we have. So this now ranges from 0 to 16 on the x-axis and from 0 to 9 on the y-axis. And then if we take the floor of this, this will just be the cells. So taking the floor means just getting the integer component. So grid UV. So this means that each cell can either be 0, 1, 2, 3, 4, 5, up to 16 on the x-axis and 0 to 9 on the y-axis. Okay, then let's take a look how we can iterate over all our neighboring cells. So essentially the idea is if this is the cell we're currently on, I want to iterate over all those neighbors and take a look inside of them. In order to do this, we need 2 for loops. So the first one is iterating over the x-axis. So you can say for x equals -1, because if we imagine the center being 0, then the one to the left is -1 and this is +1. So we're starting at -1. Then if this is smaller than 2, so from -1, 0, 1, and then the next one would be 2, so it has to be smaller than 2. And then we can say x plus equals 1. To increment this here. Okay, then we need the same thing essentially for the y-axis, so I can just copy this, put this in here. But now we're saying, okay, y equals -1, y is smaller than 2, and y plus equals 1. So what's happening in here is essentially for every cell, we're starting at x -1. So we're starting at this x position. Then y -1 is here. So we're first taking this one. Then we're incrementing that, being at 0, being at 1. And then we're done here, starting over again, doing the same thing here, checking this one, checking. So if both of them are 0, we're checking the cell we're on itself, which we also have to do. Checking this one, this one, this one, and then this one. So this is essentially what this nested for loop is doing for us here. Now that we have this nested for loop, I want to get the coordinates for the neighboring cells. So in order to get them, let's just call this one neighbor. This is the cell we're currently on, plus this offset we created here. So we can just say this is a vector 2 that consists of our x and of our y that we are computing here. Then for each of the cells, I want to get 1 point within the cell. So maybe it would help to do it like this. So these are all of our cells. And if we're where is it? Num cells. If we change this, the number of cells changes, obviously. So what we're doing now is for each of those cells, we're looking at the neighboring cells, and we're also placing a more or less random point. So the point is not really random because we're just taking the color of the cell and using this color more or less as a 2D point in space. So for each of these cells, we're going to extract one point. So in order to do this, we can say that the point equals sampling our input. So input 1. And then we can take our neighboring cells as our coordinate. This is in a range of 0 to 16 and 0 to 9. But here we need normalized coordinates, so we have to divide this by the number of cells. So essentially what I've been doing down here in order to make it visible. I will stop this here. Okay, now we have the feature point for each of those cells. Then the next thing I want to do is I want to create a vector from each pixel. So this works like a fragment shader. So this thing gets computed for each pixel. So for each pixel, I now want to get the vector from this point to the actual pixel. So this is already the start of part 2, because we're now trying to get the smallest distance from the current pixel we're on to the point that we created here. Let's maybe call this one diff for the difference, or more or less the length. So we're taking the neighbor we're currently computing, then we're adding the point that we created. So remember, this is between 0 and 1, and this is between 0 and the number of cells we have. So adding this here. And then we have to subtract the grid UV. And now we don't just want this vector, but we want the length of the vector. So we can say diff equals the length of diff of this vector we just created. And now in order to get, you know what, let's call this one diff, and this one is already the distance we're computing. So this is the difference and this is the distance. Okay. So in order to get the smallest distance, we need a global variable. Call this one the minimum distance and set this to something high. I mean, technically, the way this works, the maximum distance can't be bigger than the square root of 2. So let's just set this one to 2, just to be safe. And then I'm running out of space. I'm sorry. Okay. So then we're checking the distance. So we're comparing the distance we already created. So the distance between the current cell and the point we created. And we're asking, okay, if this is smaller than our minimum distance, which it most certainly will be, then the distance we just created will become our new minimum distance. So min dist equals this distance. So what this essentially does is it goes over all the neighbors. It checks, okay, is the current distance smaller than the minimum distance we computed? And by doing this iteratively, we get the smallest distance. Because we're always, if it's smaller, we're resetting it here. Okay. And then I guess we can already create our output color in here. But this also has to be global variable. So let's say color equals 0 for now. And the output here is also the color. So in order to get the color in here, we can sample the input, so input 1, by using the neighbor that has the smallest distance we just computed here. But again, this neighbor is in the range of the number of cells, so we have to divide it by the number of cells to be in the range of 0 to 1. And I think we also need to set the bound mode to, to clamp, so it doesn't wrap around. So maybe a bit more space here. So color equals the neighbor divided by the number of cells. So it's already working. Now you can see we have this Voronoi tiling and the colors from the input texture. And yeah, we're taking all of the 8 so for each cell, we're taking all of the 8 neighbors into account because the smallest distance doesn't have to be necessarily within the same cell. So we're looking at all the neighbors. Okay, and if I'm changing this, maybe 32 by 18, you can see how this also changes. So 160 by 90, something like that. So this is more or less what I wanted to show you. What we could also do is we could use the distance we created and take this into account here. So if we use the minimum distance instead of the color, okay, the distances are probably too big, so let's divide them by, okay. Now we can see the computed distances, so maybe we could use them and multiply this with the output color. So we can create a new variable, let's call it mask. And this one is the minimum distance. I mean, we could also just divide by the square root of 2 because this should be theoretically the maximum. And then as an output, let's say color, multiply this by the mask. Okay, so now it's dark in the center and bright on the outside. So maybe let's do something like 1 minus this. So now we get the opposite, but it's still pretty dark. So how about we apply an exponent here? So something like 0.5 or 0.25. Yeah. Now we have the dark edges on the outside and it's bright on the inside, and the color is the color from the input texture. Okay, I think that's it for this video. I hope you found this useful. Thank you for watching.